all the most important objects. So the ultimate goal is to prove a combinatorial formula for Jack characters, and this combinatorial formula involves certain combinatorial objects which are graphs drawn on surfaces, and these graphs have some extra decorations. So this is the main definition that already appeared on the previous talks, but let me quickly recall. So what we want to look at, let me just show you this picture. We want to look at graphs. These graphs are bipartite. So this means that all the vertices can be colored using two colors, black and white, such that black vertices have only white neighbors. And this graph is embedded into a surface. So it means that it is drawn on a surface. The surface can be either orientable or non-orientable. And in fact, non-orientable surfaces are the most important for this talk. And this graph additionally has certain extra decorations. So first of all, we say that it is k-layered. And this means that all the black vertices and white vertices are partitioned into sets which are labeled by numbers from 1 to k. So on my picture, these are the black labels here. And in fact, only the layers of black vertices are important because we have this condition here that whenever we have a white vertex in layer I, there exists a black vertex in layer I such that is connected to this vertex. And moreover, each black vertex which is connected to a white vertex in layer I is necessarily in a layer which is at most I. So this means that actually layers on white vertices is naturally inherited from layers on black vertices. And finally, we have the last important decoration, which comes from the fact that maybe we have several vertices in layer I, several black vertices in layer I, which have exactly the same degree. So for instance, in here, I have a black vertex of degree 2, and here I also have a black vertex of degree 2. Both these vertices are in layer 2, and this means that I need to use some extra labeling to distinguish them. So then I'm using these blue labels, such that whenever I have this situation, I number all the black vertices to additionally distinguish them. So this object is called a k-layered map. And our goal is to study the generating function of all k-layered maps. So here is this big generating function. And let us look carefully what is happening here. So I'm summing over all k-layered maps. Then I have this variable t, and the variable t tells me what is the size of my map. Then I have some other variables p's, and these variables p's they tell me what is the face type of my map. So I have a partition which tells me exactly what is the face type of my map. Then I have this very interesting statistic here, which is parameter b to some power eta of m. And this eta of m was a statistic that was measuring in a certain algorithmic way how far my map is from an orientable map. So I will not repeat exactly how this statistic works, but the main idea is that this statistic is equal to 0 if and only if your map is orientable. So whenever you have a map which is non-orientable, this statistic is strictly positive. And what exactly is this number? Well, it depends on some kind of algorithmic decomposition of your map that we described on previous lectures. And then finally, we have this last factor. This last factor is basically marking all the vertices, wide vertices in layers from 1 to k. So for each vertex in layer I have a variable si, and this is the definition of my generating function. So we want to use this generating function to prove that Jack characters are actually given precisely by this generating function. And the main idea was to use a characterization, an abstract characterization of Jack characters as shifted symmetric functions which satisfy certain properties. So there were 3 important properties. The first property, it was the property which tells you what is exactly the top degree term of Jack character, and that this is given by the power sum times some normalization factor. So we checked this on the 3rd lecture. Then the second condition says that your Jack character is vanishing on all small Young diagrams. So this was a condition that we checked on the 4th lecture. It was shown by Hussein. And there is the 3rd condition, which is actually the most difficult to prove. And this condition says that your function is shifted symmetric. So this is what we would like to do today. We would like to show that this generating function is a shifted symmetric function. So now I will start to type some new things. So let me turn the page. So one very important lemma that we used, and in general, the main idea how we could prove various things is that we found a certain collection of differential operators, and we were able to prove that our generating function is actually given by a product of certain partial differential operators acting on an identity. So we proved the following lemma. Our generating function fk minus t p s1 s2 up to sk is equal to an action of exp of b infinity minus alpha s1 exp of b infinity minus alpha sk acting on 1, where our operator b infinity of u is defined as a sum over all positive integers, t to the n divided by n, bn pu, and the definition of bn pu is the following. So this is still I'm just recalling what Hussein showed last time. So we have found the following formula, that Bn is given by the action of some operator gamma y plus u times y plus to the power n. This is an operator which involves 2 letters. So 2 infinite alphabets, the alphabet that uses variables p's, but also it uses these catalytic variables y. We're acting on y0, and at the very end, we're applying this operator theta y, which is simply forgetting all the y's. So by forgetting, I mean that whenever I have a variable yi, I replace it by a variable pi. So this formula actually comes directly from combinatorics. So this definition was inspired by a following picture. So what we would like to do, we would like to build our bipartite maps by adding stars layer by layer. And this operator Bn, roughly speaking, it is precisely what, I mean, the action of this operator, roughly speaking, it is precisely what I just said. So it is adding a black vertex with possibly some new white vertices. Whenever I have a new vertex, I mark it with a variable u. So let me make a small picture. So this is the action of this operator. So sometimes I'm adding some new white vertices. I mark them with variable u, but I also add some edges to white vertices that already exist, and the degree of this black vertex is equal to n. Okay, and last very important thing that we used to prove the vanishing condition is that additionally we have really nice commutation relations. So whenever we look at the commutator of these two operators, they always commute. So now I would like to use the formula that I have, and I would try to prove that my function is shifted symmetric. So if I use my formula, this is what I get. So fk is equal to the exponential of b infinity on minus alpha s1 prime minus 1, exponential of b infinity minus alpha sk prime minus k, acting on 1, where my new variables are shifted variables. So now si prime, by definition, is equal to si minus I divided by alpha. So my goal is to check that this function is shifted symmetric. So in other terms, my goal is to check that it is symmetric in these new variables si prime. But if I look at this formula, then I have a problem. It actually doesn't look symmetric. So at least from this formula, it is completely not clear that this function is shifted symmetric. So here's my problem. The symmetry in S1 prime, S2 prime, Sk prime is not clear. So how we would like to overcome this problem? So the idea is that we would like to understand our operators even better. So we would like to study some other commutation relations. And hopefully, if we can understand different commutation relations between certain pieces that we use to construct our operators B infinity, maybe we can rewrite this formula in a slightly more symmetric way. So this is our goal. So we would like to find more commutation relations to rewrite our identity such that it has slightly more symmetric form. So let me recall the definition of B infinity. So B infinity by definition, it was this sum, t to the power n divided by t, bn, p, and u. So this expansion, it is expansion in t. But if I look at my formula that doesn't look very symmetric, I can see that actually this lack of symmetry somehow comes from the fact that I have some shifts in a variable u. So maybe it is a good idea to actually expand this operator, not in terms of t, but in terms of u. So of course I can do this. And by doing this, I define some other operators. So now if I expand this in terms of u, I will get some other operators that now depend on p and t. And now I would like to study the commutation relations between these operators Cn's. And here is the most important lemma, which is actually the key to proving shifted symmetry. So we proved the following lemma. The commutator of Cn and Cm is almost always equal to 0. So these two operators almost always commute. So whenever n is non-zero, they commute. But if n is equal to 0, then we have this nice commutation relation that this commutator is given by a scalar of Cm plus 1. So we increase the index of Cm by 1. And this commutation relations, they hold for each m, which is strictly bigger than 0. So I'm not going to prove this lemma. Actually, the proof of this lemma is the most technical part of our paper, but I will try to explain the main ideas. So let me write. I will still write the proof, even though it's not going to be really a proof. So the proof is very technical, and it extends some ideas from our previous work. Joined with Guillaume Chapuis. And the main technique is that actually, instead of working with CMs themselves, we would like to work with something slightly more refined. So the idea is that if you remember how we defined the operators Bn, we first defined the operators that involved two alphabets. So we had Ys and Ps, and only at the very end, we were kind of forgetting all the Ys. So we had these catalytic variables, Ys, and now we would like to do something similar. So we can define slightly more refined version. So this version is when we define this operator ymn. So ymn is an operator which is defined by extracting the coefficient of u to the power m in the operator gamma y plus u y plus to the power m plus n on y0 divided by, divided by 1 plus b. So this is an operator that already refines Cn. It involves two different indices m and n, and it also involves two infinite set of variables. And then what we want to do, we want to extend the algebra by adding these catalytic variables y0, y1, y2, and so on. And then it is actually still not enough, so we continue with the same idea, and then we extend it even more. So then we somehow extend it to even more complicated algebra that uses some other extra families of variables. So now we have 4 extra families of variables. We already introduced this family of y's. Now we introduce another family of z's, z's primes, and y primes. And then we are working with these refined operators. For these refined operators, we are trying to find some commutation relations. And at the very end, we are somehow projecting everything on this algebra that involves only one infinite family of variables piece. So then we work out various commutation relations and project the algebra that involves only P1, P2, and so on. So as I said, this is really, really technical, and it's quite long. So if you are interested in the details, then this is all the details you can find in section 6 of our paper. But once we have this lemma, then I will try to show you that with this lemma, we can already prove the shifted symmetric property. So maybe before I will start to prove it, are there any questions? Okay, if not, then I will continue. So, okay. So now, once we know that we have this natural, we have this kind of natural division of this operator B infinity into C's, and we also saw that there is this very special C0. C0 plays a slightly different role because all the C's commute except for C0. So actually, it is very natural to define the following operator. So we define B infinity with this strictly bigger than something sign of U as an operator which does not involve C0. So this is a sum over L greater or equal to 1 CL times U to the power L. So in other terms, if I will add C0 to this operator, I will obtain precisely my previous operator B infinity. And now I would like to prove several lemmas that will gradually change this formula that I had before into something that will look more and more symmetric. So at the very end, I would obtain something that is symmetric in the shifted variables. So this is my goal. So my first lemma number 1, if I look at the B infinity at U plus 1, I can rewrite it as B infinity at 1 plus the conjugation of B infinity strictly bigger than 0 by exp of the operator C0. So here is the proof. Proof is relatively easy. So, okay, let me start from the definition. So I will just write that this is the same thing as B infinity at 1. Sorry. I will just write that this is just a sum over L greater or equal than 0 u plus 1 to the power L CL. Then I will use the binomial formula. So this is B infinity at 1 plus sum from k greater or equal to 1, sum for L greater or equal to k, L choose k, u to the power k times CL. And then I'm gonna use my lemma. So now I need to use the lemma that says that whenever I take a commutator of C0 with CK, then it is equal to k plus 1 times CK plus 1. So somehow the goal is that I would like to use this commutator to generate CLs by using the adjoint action by C0. And this lemma allows me to do this. So I can write that this is the same thing as B infinity of 1 plus the first sum is just the sum over k. I don't change this, u to the power k. But then this binomial coefficient NCL, I can replace it by the sum over I greater or equal to 0, the adjoint operator to the power I of C0, divided by E factorial acting on CK. But now I can use a standard formula which tells me that actually if I have an action of the exponential of the adjoint operator of something, this action is given by the conjugation of this operator by A of x. So let me write this formula. This is a well-known formula that if I take an exponential of the adjoint action of x, and then I will act on y, this is exactly the same thing as x to the x times y, a to the minus x. So by using this formula, I actually end up exactly with my statement. Okay. So the first lemma is proved. And in fact, the main technique here that we are using is we either use a Baker-Campbell-Hausdorff formula in some special cases. So for instance, if we know some commutation relation that we know that Baker-Campbell-Hausdorff formula simplifies and gives you something easy. And the main technique is to really use your creativity and try to apply this Baker-Campbell-Hausdorff formula in several places such that you somehow change your formula into something that starts to look more symmetric. So this is the first lemma that we need. And then the second lemma says that the exponential of B infinity on u plus 1 is equal to exponential on B infinity 1 times exponential on B infinity on u times exponential on minus C0. And here the main technique is precisely the Baker-Campbell-Hausdorff formula applied to a very specific case. So we have this technical lemma that I'm not going to prove here, but I will state it. So suppose that we have operators A1, A2, and C such that the commutator of the adjoint action of C to power L on AI and the adjoint action of C to power K on AJ is always equal to 0. So always means that for any ij equal to 1 or 2, and for any lk greater or equal to 0. So suppose that we have 3 operators and they satisfy this commutation relation. And then our technical lemma says that whenever we have such a situation, then exponential of a1 plus c times exponential of minus c times exponential of a2 plus c can be simplified and can be written just as an exponential of a1 plus a2 plus c. So I will denote it by red star. And the proof of this, it uses Baker, Campbell, Hausdorff formula. So now we would like to use this identity to the operators that we're working with such that we can obtain the identity stated in lemma 2. So what I would like to do, I would like to take a1 equal to b infinity on 1, a2 equal to b infinity at u, and c equal to c0. And the previous lemmas basically imply that for this triple, my assumption is satisfied, so I can use the formula for this triple. There is another triple for which I would like to use it. So another triple is the following. A1 is equal to b infinity greater than 0 at 1. A2 is a conjugation of my previous operator. So I conjugate by exp to c0, and c is equal to c0. So then by using this technical proposition, I obtain the following formula. Exponential of b infinity 1 plus c0 plus the conjugation of b infinity e2 minus c0 is equal to. So the first thing is that I'm going to use my proposition. So I write it as a product of 3 exponentials. So it is exponential of b plus 0 times exponential of minus c0 times exponential on c0 plus e c0 b infinity on u e to the minus c0. And now I want to rewrite the last factor. So here I'll just repeat. I don't change these factors. But the last factor can be written such that C0, because C0 commutes with exponential to C0, so I can simply write it like that. I can conjugate everything by e to the C0. And then I can recognize that what I have inside is just P infinity on U without this strictly bigger than 0 part. So here I just continue, I write exactly the same thing. And then I just write that the last part, it is just the same thing as e to c0 on P infinity on U e to minus c0. And finally, the very last thing to do is to notice that if I take the definition of exp, so I'm interested in this part, and if I take the definition of exp, it involves taking this operator to power L. And I simply notice that if I multiply it by exp to the minus c0, I can commute it on the other side. So let me just write what I just said. So now if I take exp on minus c0 times e to c0 p infinity on u e to the minus c0 to some power L, this is actually the same thing as p infinity to power L times exp to the minus c0. And therefore, we deduce that exp of p infinity of u plus 1 is exactly what we wanted to prove. Okay. So once we have these two technical lemmas, we're actually ready to prove the shifted symmetric property. And to be more precise, we are going to prove the following formula. So we claim that Fk on minus t p s1 up to sk can be written as follows. So this is an exponential of p infinity on k minus 1 exp on p infinity 1 times exp of the following operator c0 plus p infinity on minus alpha s1 prime minus k plus oh, I don't have space here, sorry, plus p infinity on minus alpha sk prime minus k acting on 1. So the main message here is that we were using many different commutation relations between certain operators that we used to build this more rich operator, such that we could start with the previous formula and we can rewrite it in a way that first it involves exponential of some operators that does not involve any s's, okay? So we have this part here, which does not involve any s's. And then we have an exp of a sum. And this sum is clearly symmetric in SI primes. So I can exchange SI primes and this sum will not change. So if I can prove this formula, then I can conclude the shifted symmetric property because this formula is manifestly symmetric in SI primes. Okay? So how the proof goes? So there are several steps. So the first step is that so by the way, the proof will be done by an induction on K. So the first step is that we need to check the initial condition. So the proof is by induction on K. And when K is equal to 1, there is nothing to check. So this is a trivial case. When K is equal to 2, then there is something to check. So the previous lemma implies that P infinity at U plus 1 times P infinity at V is the same thing as P infinity at V plus 1 times P infinity at U. So the previous lemma, it implies that we have this kind of interesting commutation relation. Again, I'm gonna use some color to mark it because I will need it. So I'm gonna use this commutation relation to check that F2 is given by the formula that I claim. So if I take F2, then F2 is just exp P infinity minus alpha Si prime minus 1 times x P infinity minus alpha S2 prime minus 2 times 1. But then I can use my identity and I can rewrite it as exp of P infinity minus alpha S1 prime minus 1 times exp P infinity minus alpha S1 prime minus 2 times 1. So I'm good. So now let me move to the first step. So sorry, to the second step, which is the inductive step. So I take f k plus 1 and I'm going to write it as exp of P infinity minus alpha S1 prime minus 1 times. And then I'm going to use my inductive hypothesis. So what am I doing here? One comment. I'm just using the formula that I used at the very beginning. So we had this formula which was not symmetric. So my first exp is the first exp from a non-symmetric formula. But then I can recognize that the product of all the other exps is just fk So now I can use an inductive hypothesis, and I can write it like that. So this is exp at p infinity at k minus 1, exp at p infinity at 1 times exp at c0 plus p infinity greater than 0 minus alpha s2 prime minus k minus 1 plus p infinity minus alpha s k plus 1 prime minus k minus 1, and everything is acting at 1. But now I'm gonna use my, so now I'm gonna use my, I'm using this star, blue star, k minus 1 times. So what I want to do, I want to take the first exp and I want to commute it with everything which is on the right. So I have k minus 1 operators and I want to commute it with all these operators. And I can do it using my commutation relation. So if I do this, then I end up with this formula. So each x is gonna increase b infinity at I minus 1 into b infinity at I. So I will have the product of these guys. Then I have my operator that I commuted on the right. And because I commuted k minus y times, so it changes into b infinity minus alpha s1 prime minus k times, and then I have the same factor as before. So I'm just gonna repeat it. I'm not changing it yet. So c0 plus b infinity minus alpha s2 prime minus k minus 1 plus b infinity minus alpha sk plus 1 prime minus k minus 1, which is acting at 1. And then what I want to do, I want to use this other lemma, lemma 2, which allows me to replace this thing, so this thing, by lemma 2 is equal to exp at p infinity 1 exp p infinity minus alpha s1 prime minus k minus 1 times exp at minus c0. And then if I use this identity and I plug it into this identity, I end up with something that I want. So finally, exp of p infinity minus alpha s1 prime minus k minus 1 times exp minus c0 times this very last part that I had there. So it's c0 plus these guys minus alpha sk plus 1 prime minus k minus 1 is equal to And here, again, I'm going to use my lemma too. So this is equal to exp of C0 plus B infinity at minus alpha S1 prime minus K minus 1 B infinity minus alpha SK plus 1 prime minus K minus 1, again by lemma number 2. So this is the end of the proof. Phew. So this proof was it was maybe quite technical, but the main ideas are that basically we can start with a combinatorial object. We write a generating function for these objects, and we can try to think how you could build this object using certain partial differential operators. So what you do, you somehow try to mimic a combinatorial combinatorial decomposition by analyzing how you can apply certain differential operators to an alphabet that mimics exactly your combinatorial decomposition. And it turned out that this is a very, very powerful tool because this allows us to rewrite a combinatorial function as a certain product of quite complicated operators acting on one. But then we can study all the algebraic relations in a certain algebra where our partial differential operators live, and then we can try to rewrite it in a way that it has the form that we really want. So remember that we really wanted to see something which is shifted symmetric. It was completely not clear from the combinatorial definition that you can get something that is shifted symmetric. But then you can see that using a richness of this algebra and the fact that there are many interesting commutation relations, you could try to somehow massage your formulas and transform them into something that is manifestly symmetric. Right. So let me just finish by actually stating this main theorem again and making a quick summary. How did we prove the main theorem? So finally, we can conclude the main result. So again, let me recall what was the main result. So the main result was that if you look at the Jack character and you want to compute it on a partition lambda, it is equal by the following combinatorial formula. So it's a sine, then you take a sum over all layered maps, and we have B to the measure of non-orientability, 2 to a combinatorial factor times a product of minus alpha times lambda I to the number of white vertices in layer number I divided by the normalization factor. So how we can prove this? Well, the only thing we have to do, we just have to check that all the conditions from the characterization theorem are satisfied. So the first condition says that if you take my generating function of layered maps and you check that if you take a generating function of k plus 1 layered maps and you kill the last variable, you will obtain a generating function of k layered maps. And if we add to this a condition that we just proved, namely that f of k is shifted symmetric, then we can conclude that F infinity, which is defined as the projective limit of Fk, exists and belongs to an algebra of shifted symmetric function, of a polynomial with the coefficients which are shifted symmetric functions, and it's a polynomial in T, P1, P2, etc. So now I know that F infinity is equal to the sum over all not k-layered, but just layered maps. P, here is a partition of the face. Then I have the standard. I have a standard thing, so 2 to the number of vertices minus connected components, alpha to the number of connected components, and my product and then once I have my function, which is well-defined, it's a well-defined shifted symmetric function, then in the second step, I can just check all the conditions. So the first condition is that if I extract the coefficients of T mu, P mu in F infinity, this is a shifted symmetric function. The second condition is that if I look at the top degree coefficient of T mu, P mu of F infinity, that this top degree coefficient is equal to alpha to the power mu minus L of mu divided by Z mu times P mu at lambda 1 up to lambda k. This condition was checked by Hussein at the third lecture. And then finally, the last condition is that, again, if I take the coefficient of my generating function and I compute it at a partition which is small, then I've got 0. So this is small for all lambdas, which are slightly smaller than mu. And this was again checked by Hussein on the lecture number 4, and we are done. So using characterization theorem, our coefficient of F infinity must be equal to the Jack character. Okay. So thank you very much. I think that today's lecture was quite heavy because the most difficult stuff was left for the last lecture. So if you have any questions, please go ahead.
Yes. Well, first, let's thank Maciej for a great lecture. And any questions here?
May I ask one?
Yes.
So the proof technique is basically doing sort of like algebraic induction, right? But as you said, you're trying to have this like combinatorial object and then translate to find an algebraic object so that you can do algebraic proof. But then have you tried to kind of decode what you're doing in the algebraic proof and see what happened to the actual algebraic structure that you have and see what is actually going on in the combinatorial structure?
I'm not really sure if I understand.
No,
the
so
question.
basically it's like I have a you have a combinatorial object and then you translate to algebra, right?
Mhm.
And then you prove everything using different algebra, like identities and lemmas that you have shown.
Yeah.
So what if so I just wonder if you have tried it to kind of translate what you have in the algebraic proof back to the combinatorial object and see what is actually happening to the combinatorial object.
Yes, yes. Okay, I see. Now I understand. So yes, this is a very good question. So for instance, whenever you look at all the commutation relations that we are trying to prove, it is very natural to think about this action. So of course, each operator somehow came to us from combinatorics. So this means that we understand that a certain operator does something to our combinatorial object. Then we prove some commutation relations, and you could ask why these commutation relations hold, like from combinatorial point of view. And it's interesting that some of the commutation relations we can see combinatorially, but some of them are actually not so clear, and we don't fully understand actually why they hold. One big difficulty is working with B. So for instance, if B is equal to 1, we don't have this measure of non-orientability. Combinatorics makes sense, it's easier. Your commutation relation also makes sense, they're also easier. And sometimes we can see more easily why certain commutation relations hold. When you're working with B, it's more complicated because if you remember, the way we define this measure of non-orientability is quite complicated. So there is this algorithmic procedure. So whenever we are trying to commute some operators and you try to think, what does it tell you about your combinatorial object? It tells you many non-trivial things, that maybe if you do something, your measure of non-orientability is not changed dramatically or things like that, but a priori it's not clear why. So I mean, I don't really know if I answered your question, but
no, that's great.
we,
Like that just means that like there are lots of things that may be hidden in the combinatorial object that people can try to work on as well, or maybe translate the combinatorial object to an other combinatorial object that may make everything looks clear.
Yes, yes, definitely. So for sure, some of the commutation relations, in fact, they really come from combinatorics. So the way we thought about them is that they should be true because of what they're actually, what they do combinatorially. Some of them were really obtained just using algebra. And
I see. Thank you.
We're familiar with this phenomenon when we work with Macdonald polynomials. There's a lot of operator relations which are simple to write down, but you try and understand the combinatorics, and it's just horrific.
yes.
So, yeah. Any other questions? Yeah, I see a lot of people nodding their heads. Yeah, any other questions?
There's someone in Q&A.
Oh, here we go.
So is there a hope for, oh, actually, do you want to unmute and then ask the question yourself? Oh, never mind. I can read it. Oh, I'm sorry. So I'm not sure if I know how to pronounce your name, but so there's somebody in the Q&A asked it, is there a hope for seeing the shifted the symmetricity combinatorially? Yeah, I think it's
If we can see
yeah.
this shifted symmetric property combinatorially,
Right.
oh, we would really
So
like to,
like
but
like the guest says that like for example by exhibiting some involutions at the level of maps of something like that.
I think it's very, very hard. I don't know how one can see this shifted symmetric property combinatorially naturally. Maybe Hussein has some ideas, but I think it's going to be a very difficult thing. So you can see that algebraic proof is actually very, very difficult. And you know, we are doing it this way because we do not really know how to do it combinatorially. So yeah, I think that combinatorially it's a very hard problem, but maybe
Yes,
Hussein wants to add
I think
something.
for the shifted symmetry property, there is for alpha equals 1 when we are working with only orientable maps, or alpha equals 2 when we work with non-orientable maps but without these weights. I think that there is a way to prove this shifted symmetry property by proving that we can add vertices in different ways. So instead of adding two vertices of degrees n and m, maybe we can just add one vertex of degree n plus m plus 1 or something like that. But these kind of arguments, they really don't work when we have the non-orientability weight. So for example, for the vanishing condition, there are proofs which are have been used by Ferre and Schniade when alpha equals 1, alpha equals 2. But again, they do not really work when for general alpha.
So just maybe additional comment. This is related with the fact that there are many ways you can try to define this measure of non-orientability, but if you do it in the wrong way, it just doesn't work. So you really have to do it in the correct way. We have this very specific combinatorial way to compute the measure of non-orientability. And so it really matters. Where do you start from? How do you proceed? And so on. So then you can think that if you will try to add vertices in different order or something like that, maybe it will affect heavily how you compute your measure of non-orientability. And this is a typical problem actually here.
Hey, any other questions or comments? Okay, let's thank our speaker again. And I believe Maciej is going to finish off the series on Thursday.
Yes.
Right? Okay, great. So
Thank you
we'll
very
see
much.
you all Thursday. Thanks again.
Thank you.
Thank
Bye.
you.